Yeah.
I have some extras if anybody needs.
In the depth of when
So badly. Especially color ones. Coloring is not.
Yeah, it's big for me.
Whenever I have a handout, I always take a picture.
That's
So I will eventually lose.
I've lost like every handout I've gotten this semester. I know.
I clean out my room and I'm never going to need this again. And then it's just like, oh, remember that handout I gave you like 4 weeks ago?
You need it.
You need it now.
All right, guys. So you remember this handout, right?
Yes.
It's Jeff's most colorful handout ever. I'm going to put it in the museum. So this very last problem, I want to try to set it up both ways. Because there are a lot of problems where you can do it both ways. There are some where it's impossible to do. So we're going to focus on those in a minute. Let's see. This one I could actually do it both ways. If I wanted to use the washer or disk method, right? I don't have to go in knowing. I just want to try to use the disk method. Who's got this down yet? For the disk method, I'm going to rotate this region. I've already drawn it for you, even colored it in. I'm going to rotate that about the y-axis. So if I want to use the disk method, it's going to be integral dy. I like it. Why does that seem like it might be harder than I want it to be?
Because everything is related to x.
Because it's given to me as functions of x. And if I want to do I'm going to call it the disk method, although we can see it's going to be a washer. Who gives a crap? It is, the washer is disk, right?
Minus whatever.
So integral dy. So what do I have to do with these guys first if I want to do the disk method?
Y squared.
Sure. And then what would this be?
Y squared.
Y squared plus 1. What would this be?
The square root of y
Y
plus 1.
plus 1.
X equals square root of y plus 1. Nice. Alright. And then how does this disk method work? It's built off of what shapes, what geometry of what shapes?
Circles.
Circles. What are the circles?
The area.
Area of the circle. So just remember it's pi r squared. How many radii do I have here?
2.
Where do they start? The radius is
On the Y.
1.
yeah, the y-axis is what I'm rotating around. So I draw out, and the first thing I hit, that's going to be r
First.
The bottom.
R inner.
Yeah.
So our inner is going to be this guy, and our outer is going to be this guy. So how do I set this up? Pi times what goes inside?
The square root of y plus 1.
Minus ri.
Squared pi r squared minus pi r squared.
Yeah.
And minus this guy is going to be the empty region, right? Yeah, minus y squared plus 1 squared. So that's completely doable, right? That wasn't too bad. It wasn't difficult to solve for x. I needed functions of y, because for that method I need integral dy.
So it's outer minus inner.
Yeah, it's r outer
Minus R inner.
minus r inner. Did I right? Yes, good. You want to take the outer one, the big whole thing, minus the empty middle. Yeah. How are we doing so far? Is that all right? You're carving the middle out. When I do this, that's carving that empty part out. All right, and that we could do. We could FOIL it out. That's doable, right? What would the limits be on the integral?
1 and 2.
0, 1.
Yeah, it's dy. That controls everything.
0.
Yeah, what's y doing 0 to 1? I love it. I love it. So now, we just learned shells the other day. Or, we talked about them.
They were brought up.
Learning takes a while, right? But we talked about it. If I want to use shells, whatever washers would be, shells is the opposite when I set the integral up. So washers would be, or disks, whatever, would be dy. So shells is going to be dx. Because if I can do shells, I want to rotate this thing about the y-axis. So to draw a representative rectangle, I do it parallel to the axis around which I am rotating. Whoa, let me say that again. So this is what you need to wrap your brain around. If you don't want to make it pure memorization, which I hate, you want to make it, this is why it makes sense. This is why one is dy, one's dx. There's a representative rectangle that's going to rotate around and become a shell, right? Going to rotate that boy. It's going to be a giant ring, the ring that you put on, the ring to rule them all that kind of shit, right?
Yeah.
Yeah, it's huge, man. It's like so on. Wore that thing last. Sorry, that's like majorly geeky and creepy. Yeah. Sorry. So that is an example rectangle. I would definitely draw this bad boy. It's going to be always parallel to the axis you're rotating around. So how do I locate it? It's located using the x-axis, right? If I drew another one there, then it's somewhere else on the x. So you locate them, and this is what I said earlier in the little paragraph. You locate them on the x-axis. The axis is parallel to the one you're rotating around. Because you're going to have a rectangle, you're going to rotate it around. How do you locate that? On the x-axis. That's how I locate it. Because that's why for shells on this problem, the integral dx. Because as you move along the x-axis, from what to what?
1 to 2.
I'm picking up all these rectangles that I'm going to rotate as I move along the x-axis. Why was the other one the way it was? Because I'm making these circles as I move along the y-axis for the washers and discs. I pick up the circles. Do you see? If you can, the more you can see that, that's what to focus on. Or just make it pure memorization. You're only going to get so far in math because your brain's, if you've done that so far, I don't know how your brain has any room left. Mine would not. So, shells, I know it's going to be integral dx. I know it's shells, so it's going to be the circumference of 2 pi r. Right, how are we doing so far? So I can put that 2 pi out front. We already said what the limits are going to be, right?
0, 1.
Say again, sorry?
1, 2.
Yeah, x is going from 1 to 2 to pick up the whole region.
Right.
And then what's the radius of this problem going to be? What's the radius? How do I locate this? Where is this located? How far away from the axis is it?
It's from the x-axis, right?
So whatever that specific x is, that's what locates it.
Yeah,
right?
so that one's going to be...
So the radius is just going to be x
X1
at 1 to 2. Anywhere from 1 to 2. Whatever x is, that's how far away that shell is. That's the radius of that shell. So r is going to be... so we're doing 2 pi rh dx. So we got 2 pi there. Radius is x. What's the height? How tall is that rectangle I've drawn?
X minus 1.
What's the top of the rectangle?
Isn't that the... Oh, it's...
What's the top? What's the top of the rectangle? This is the top here, right?
Yeah, that's the function.
Square root of x minus 1, right?
Minus
So square root of x minus 1 minus, how tall is this? So that's the top, and what's the bottom? X minus 1 squared.
So the width is some variable x. It can be anything from 0 to 2, right? That's what we were just talking about.
Yeah, so as I move along the x-axis from 1 to 2, I'm picking up rectangles that I'm going to rotate. Right? The dx is the thickness to make an actual volume, so I'm adding volumes up. So that's this idea of thickness. But I am just doing shells. This is infinitesimally small, so it is basically like outside of a cylinder, right? Like you unwrap a Campbell soup can. There's the area I'm talking about, but I multiply by the thickness to make it a volume. So I'm adding up all these volumes.
Right.
What's the radius again?
Radius is always how far any rectangle would be from the axis.
So any number from 0
Yeah.
to 2.
So if I was rotating around x equal -1, the radius would be what?
X plus 1.
X plus 1. It's x plus 1 away from that axis. And the beautiful thing about shells is there's just shells. There's no shell empty bits in the middle or something, right? I don't know what the washer. There's no washers. Shells they just don't pick it up. They just don't put little rectangles there. If it's empty, there's no rectangle there. It's nothing. So it doesn't have to subtract anything. Wash discs are just sort of single-minded, like, oh shit, there's some empty. We better subtract some of our. No, shells are just very direct. They're like, we don't even make a rectangle. There's nothing there. Oh, that makes sense. You can tell I kind of like shells better. But discs, of course, work sometimes when shells don't. Both of these will work. Does this look at all familiar? This first piece?
X.
That's right. So that's doable. But again, which one of these is easier just to do straight off? This one actually is. I can foil that, and then I can do it. This one takes a little bit of U subs finagling. Yes.
Why is there an X on the outside?
Oh, so it's okay. So let me do this. So for shells, it's going to be the integral 2 pi. Can you see that? No. 2 pi r h dx. I really want this to make sense. This piece is unwrapping a Campbell soup can, and that's the area of the label. right? It's 2 pi r times h. That's the area of the label. Dx is the thickness to make it a little tiny volume element. So the 2 pi doesn't matter. I love 2 pi. R is how far away any rectangle would be. So that would be x. X controls where the rectangles are. And this part tells me that pretty much. Right? If that's dy, it's going to be based off of y. If it's dx, it's going to be based off that. There's no way. It's just that the axis is not one of the y or x axes. You might have to do +1, -1. Right? Like we just did, yes.
So if we were doing a problem where it was removed from the x-axis, would the r be like x - 1 or x + 1 or something?
I'm sorry.
Yeah, so if it was like 1 this way, it would be +1.
So there it is, written a little bit
Why
better.
is H
Because you're trying to get back
Say
to
again?
either the x or the
Why
y.
is H?
Yeah, that's what I was saying.
H is the height of any rectangle, and how tall is the rectangle? The top function minus the bottom function. That feels like the section where we found the area between two functions. Yeah,
Okay.
I like it. So shells has troubles with certain intervals because it introduces this extra little piece here, right? This extra variable. So you guys might realize that'll throw some things off. Some things won't be on hell. This one you can do. If I couldn't do it, I would just set it up instead as a disk, or in this case a washer, and do it that way. So this is another situation in math, just like in pre-calc, when you remember trig identities. This is like your first major thing where it's a part of the whole experience is to make mistakes. It's a part of it. And to be able to go, I didn't want to go that way. Let me go back and try another way, right? So this one, if you set this up and you're like, I can't, that's not possible. All right, scratch it out, go do washers or discs, right? You just don't freak out. That's part of the process, is to write something down, and then that's the only time you can see that it's impossible is once you get it written down. Yes?
Is the main part of this problem to just set it up, or will we need to solve it?
Oh, so I'm hoping solving the interval will be relatively simple.
Because, yeah,
To me, the setup is the hard part. Well, I already did this first part here, right?
that's solved.
I kind of knew it was coming, so I wanted. So this is how you would attack this. You distribute the x through, right? Then you FOIL this out, multiply by the x. Is that cool? I mean,
Why is the art X again?
so watch this. All right. So if I cut this bad boy in half, it's this here, right? This green,
Yeah.
right? Is that cool? So what's the radius of this? It's how far it is from the axis to any arbitrary rectangle, and how far is that? You can't really see
So
that too
X is just X.
well. That's better. Okay. Yeah, it's just x.
So it'll always be X?
No, it won't. If I'm rotating around the x-axis,
Yeah, I mean, for a shell like this, it'll always just be
yes,
X.
I want you. If it's dx, it'll always be x or x plus 1. If I rotate around x equal -1,
Oh, okay.
then how far is this to that rectangle? X plus 1? Does that make sense?
Rotating around 0, it's just X.
But if you're rotating
The
on the
moment
y
that
axis,
Don't worry. I have planned to do some examples. We haven't done a lot of axes that weren't the y or x axis. So let's do one of those. And then I want a lightning round of setting up integrals. Yes?
Just so for a shell, you're making it and you're peeling it off, and that's what you're finding. Versus a washer, you're building it and cutting it in half and taking that piece out.
Yeah, so I love the idea of, they often call washers and discs slices, right? Where shells are just shells.
Yeah.
So slicing it up is sort of like you have a big chunk of meat, you're slicing it up.
Taking a piece out and
You know,
saying,
you want a jelly fin, you want a thing, right? You're slicing it up, and then you can put the slices back together to see what the volume was. Shells, there's no real good physical analog.
the Campbell's soup can, you take it off.
An orange peel.
I always think about like the stacking bowls, the mixing bowls you stack, right? So you can stack them up. It's sort of like that. I mean, but they sit inside each other. It's a little bit weird, right? It's a little bit strange. This process here, there's no good physical analog to that I can think of. Sorry, math doesn't always have a nice physical analog. All right, so let's do this. Let's try a problem out of the book. I don't recall. I don't recall asking for requests. Let's see what 12. Just 12?
On 6 too.
No, I'm in 6-3 now. That's too bad.
Nice try.
I definitely want to do one where the axis of symmetry is not x or y axis. So it doesn't really matter here. Let's see. This one looks yellow.
Well, it is the x-axis.
What's up?
That one is on the x-axis.
No, this is x equals 2.
Yeah, but about the y-axis. I mean, about the x-axis.
Oh, these are all about the x. I thought this was about the, okay. So let's do this. This is what I want. Thank you, Micah. I thought they were saying about this. So here, let's do 15. No, I'm off 15. And I said let's do it, so let's do it together.
As in me.
Alright.
Is in you.
So I gotta use shells. Because they tell me to. But we'll see if we'll do it by shells first, and then we'll see if washers or discs would have worked. So 15, if we draw that bad boy. So y equals 0 is also known as the x-axis. Cool. X equals 1. Where's x equal 1?
It's 1 over vertical.
Alright, so this here is the x-axis. And y equals x to the 4th. Well, that's nice. 0 and 1. Whoa. So this area here, that region, alright, how do we know so far? So I mean, what sucks is when people can't draw that region, and then it throws them off later in the problem. You actually could do this problem without drawing the region at all. It would be really not easy. But I hate it when regions are what throws people off. Draw the region well. I'm rotating about what? X equals 2. So this is my axis of rotation. I'm going to rotate this bad boy around like that. Right, so I'm going to end up with like since the time is coming, I'm going to end up with like a Christmas tree. What do you call it? Base, right? Stand. Does that make, can you guys see that?
I see.
If you rotate that bad boy around, you're going to have a nice big old Christmas tree fitted, fat thing, yeah. Right, if you can afford it. Or just screw that screws all the way in so you can get the little tiny scrub thing that Jeff could afford when he was in college.
Wait, is that one?
Say again?
Is that y equals 1? Next to 2. Is that what?
What's happening?
Or x equals 1, sorry.
This is x equal 1, yeah.
So this could be a washer or shell.
Well, let's see. We're going to do shells. If I do shells, what would integral d what? What would
dy.
So I'm rotating around something that's parallel to the what? Y-axis.
So it would be dx.
So
One of the
discs would be dy, therefore shells must be
dx.
dx. I like it. Let me stop there for a second. So if you're having trouble remembering, just remember that discs are integral d whatever is parallel to what you're rotating around. So then you've got shells, start there and just go, it's the other one, if you need to. Alright, so that helps me out. So I want all my functions inside to be functions of x. Cool. So if I draw a representative rectangle, I'm rotating around this way, so here's my rectangle.
Bam.
Bam. Now here's where things get interesting. Let me see. Hopefully you guys don't think it's too freaky, but where do I start drawing my radius? Here. Good. So how? Now this is where things get interesting.
X plus 1?
X minus 1.
X minus 2.
X equals
Yeah, x minus 2.
X minus 2.
So how far away?
X.
It's 2 away from the origin.
If x was 0.5, how long is that?
0.5.
Think about it for a second. Yes, 1.5, isn't it? If my rectangle, let me draw this a little bit bigger. So here it is. Let me just cut to the chase. Wow! And then here's my axis of symmetry. Okay, big old thing we can look at. So if I draw a representative rectangle, this is x. This is my radius. This is 2. If this is x, this must be 2 minus x.
Because you're going back.
I mean, that you absorb it. Because the radius is the length from the axis to a rectangle. right? That's the radius.
So the radius is 2 minus x.
Yes, because I got to go from the axis to the rectangle. If this whole thing is 2, and this is x, and this is 2 minus x. How are we doing so far? So whenever the axis is not the y-axis or the x-axis, that step is going to get harder. You got to actually draw it well and think about it, right? It's not going to be a gimme. If it's the x or y-axis, it's a gimme. X, Y, I'm done, yay, you know. But if it's not the x or y-axis, you got to think about it for a second.
When would it be the other way, like x minus 1?
Oh, if I was rotating something around here, it would, well, that would be a little strange. Oh, yeah, sure. If I had, for example, this, go with me for a second, and I was rotating about x equal 1, then how long is this? That would be x minus 1, right?
Yeah.
All right, cool. All right. I like it. Good question. All right. So there's what's going on. Drawing in a representative rectangle is a very good idea, because then it can label what the hell you're talking about. That's the radius now. That's r. So remember, what I'm trying to fill in here is 2 pi rh dx is there. So we got dx, we got 2 pi out there. I just need r.
Which is 2 minus 1 x.
Now, what's the height? This one's not too bad at all.
The function
X to
of
the
x.
fourth minus. Just X.
Yeah, it's just x to the 4th, right? Is that cool? X to the 4th minus 0. Because it's actually on the axis. It's nice. So you guys with me a little bit.
Mm-hmm.
So the other one had the rectangles floating. So the height was the top minus the bottom, but the radius was easy because it was actually rotating around one of the main axes. I don't know if you guys remember. This one's the other way around. The height's easy because it's just a function, but the radius is funky. All right. So now I've got everything identified. I've got my 2 pi there, my dx there, my radius is there, my height is there. And now I integrate. Now this should be the easy step.
It's from 0 to 1, right?
Oh, good. X is going, so it's dx, so x is going from 0 to 1. Kick ass. I like it. So now you just got to integrate. So if I distribute, that's a beautifully nice integral, right? A gather integration sign, we can integrate.
X over 5.
2x to the 5th over 5 minus x to the 6 over 6. That should be the easy step. So then when you click 0, it's going to be all 0, so it all depends on 1. So it'll be 4 pi over 5 minus 2 pi over 6, which is pi over 3. Let me stop there for a second. The last 3 steps are the easy part of the problem. Should be. Oh, sorry. All right, let's try to set this up as a washer problem. Or what are we rotating around? Yeah, it's going to definitely be a washer problem. Let's see what the difference is. Everybody cool with that? You guys got that? Oh.
So in the washer problem, the radius is both. You have 2 radiuses. You're subtracting one from the other.
2 radiuses.
Radii.
Alright. So.
Is this
washer.
English? No, it's
So I'm still rotating around x equal 2. So if I want to use discs or washers, it's got to be integral d what? dy. Put a little pi outside because I know the inside's going to be the r stuff, right?
Wait, is this for discs?
This is for, yeah,
washers.
I like it. Alright, so if I start drawing from the axis out, as always, that's going to be our inner. That's going to be our outer. So what is this? 1. It's always 1. How far apart are those? Well, this is 1. They're 1 apart. Yay. 2 minus 1 is 1. Yay. So it's always bigger minus smaller. Do you guys see that? So up here, this was 2, and this was x. That's big minus small, 2 minus x. Because it's got to be a distance. It's got to be actually, it can't be a negative distance. It's weird. It's in you. It's in a black hole. I don't know what that is. I don't know. What's the radius outer going to be? It's going to be 2 minus
X to the 4th.
Yeah, so radius inner is 1. Radius outer, 2 minus x to the 4th. I like it. So watch. You can check yourself. When x is 0, how long should this be? It should be 2. When x is 0, it is 2. It's crazy. Okay, maybe. You can always check yourself. Just take some extremes or take some examples. Make sure it actually comes out to what it's supposed to be for a concrete example. Because this is definitely not concrete. Okay, so then I can just go to do my r outer minus my r inner squared. Right? So pi r squared minus pi r squared. Let me stop there for a second. Yes, sir? You good? And this is relatively simple, right? What's my limits going to be? It's got to be what y is doing, and of course y is doing the same thing that x is doing, 0 to 1. I like it. Doesn't always happen that way, right? Just happen to be that way here. All right. And if we integrate this, let's see, we should get the same thing we got before. Let's see if we can do this very quickly. 0 to 1, 4 minus 4x to the 4th plus x to the 8th minus 1 dy. Right. There you go, Jeff. So I get pi times 3y. Wait, why do I have x's and y's? What's happening here? Yeah. Okay. Good job, Jeff. Pay attention to your dy. I need this to be a function of y, of course. So what is that going to be as a function of y?
2 minus this.
Let me make sure you guys are with me. The whole reason we do this, and I just powered right past it, was to remind me that I have to put functions of y in here, right?
How would you draw your reference rectangle?
Oh, there's no rectangle for dishes. Wasters or dishes.
Dosters and wishes.
It's just these. So this is understood to be there, right? With the empty middle. That's a horrible picture, but so this, of course, is y equals x to the 4th, so it's x equal to the 4th root of y. So that should be what I have here, the 4th root of y. Let me see. Let me make sure you guys are with me. Because if I'm doing it with disks and I'm rotating around something parallel to the y-axis, I have to do integral dy, which tells me I have to have functions of y inside. Right? So it was my fault. I just powered through with a function of x. Of course, now the beautiful thing is, you catch yourself pretty quick. That's x, and I'm like, oh shit, I can't do that. No. I like it. So I can pretend like I did that on purpose, but it's too late for that. I've already admitted it. Which is fine. And so what should this integral look like? It should look like pi integral 0 to 1 r outer squared minus r inner squared dy. So you can that's still easy from the idea of an integral. Are you guys with me? I can FOIL that out. It's not bad. It's all powers of y. It's easy integration. All right.
3 pi.
Yes.
So r of 0, is that supposed to be r initial?
That's r outer
R outer, okay.
and r inner.
That's 4 root y.
I'm sorry? Do it again?
Yeah, the outer is 2 minus 4.
2 minus 1.
I'm just trying to figure out where the 4 root of y is coming in. Like, is that supposed to be?
You have to put it in terms of y, and then your outer function is the x, or the y.
Oh, okay.
Are we good?
Yes.
Okay. All right. Because so what I want to focus on now is, let me see, where was that guy? Okay, let's do this.
So So what I'll just do the rest of that. It's time to
No. It looks too easy to keep going. I don't want to waste her time. Foil. It's just y to the 1/4 and so forth. Right? Integration should be easy after this. We better get the same answer we got there, or else it's going to be trouble. All right. So you guys take a minute and try to do number 16.
Cool.
Try to set up number 16.
As a shell?
Yeah, as a shell. Yeah.
Y is the square root of x. It looks funny when you look at that. There's like 0. X is 1. Something like that. X is equal to 1. X is rotation. Here's X. Greater than minus 1. X minus 1. X plus 1. Doing x plus 1 times this one.
Would it only be x minus 1 or x minus 2 per hour? On this?
What are you going about?
The radius is x plus 1.
X plus 1?
Just like the example we did earlier. It's around x equal -1. Yeah. So normally it'd be x. We're going to add that extra bit so you can actually make it to the axis. It's a rotation.
This far away. H
From
You guys done?
No.
No?
What?
So then work on it.
Registration.
It's amazing. Hoping the little elves come, little calculus elves.
0.
They are hoping.
That'd be nice. It's just
1 plus 1 is 2. 2 times 2 pi is 2 pi.
what did you get for that integral? I got 2 for that. X to 3 over 2. 3 years. Oh, after you foiled it.
Yeah.
After you foiled it.
Because there's no other thing. There's no other function. It's just 0 and it's the root of x. And then you have 2 pi.
5 plus 1. Okay. Yeah, let's just factor out R. What's the y equal to? X to 2.
Yeah. Root of x, x equal 1, 2, and you're rotating around this one, right? Yeah. Good. Using shells.
0, 1 with my
So then starting from here and drawing out along,
be 2 over 5
and draw a representative rectangle.
plus 4 over 3.
Yeah, so it's going to be, so that rectangle sits at x. So how far away is it to that? How far? Okay.
4
It is minus plus 2 if it was already there. So you're drawing a representative rectangle, so it could be anywhere. So it could be right there. So it's not always 2, is it? So what is it? This is just some x. So how far is it?
You have to.
Good. That's right. Cool. So don't make it too specific of a rectangle. It's got to be any possible rectangle.
Well, I just distributed last because it's easier to deal with those 2 piles.
But you're rotating it around.
Yeah.
So it should be dx.
Right.
you're doing washer and shell,
You graph it like that.
right?
Is that fourth?
So
Yeah.
since it's parallel to the y-axis, washers would be
X to the 1/2.
dy.
So-
We're doing shells, so
So this would be
it's going to be the opposite.
X to 1/2 times 2.
Wait, where'd you get the two?
Oh, it's stopped.
The 2 came from the X.
Oh, okay.
It's 16, right?
Yeah. Yeah. It's,
Okay.
it's X plus 2 because we need to go from here to here, right? So X plus 2, and then when you distribute it here to here,
I thought it was bigger minus 1, so x plus 1.
yeah, X plus 1. Or no, it doesn't go to the X-axis, it goes all the way to here. And that's 2 away. 1, 2. So it's X plus 2.
Well, this is not too bad. Oh, about x equal negative.
Yeah.
It's x plus 2? The radius?
No, hold on.
It's not.
Nope.
It's x plus 1.
All right, here we go. Ready?
Yeah.
Let's take a look. So it's going to be integral d what?
dy.
No, I thought it was zero.
It's dx. You with me? Again. Definitely have it set for discs. Discs are easy. If they're going around, anything parallel to the y-axis is dy, x-axis is dx. So this is parallel to the y-axis. Discs would be dy, therefore shells must be dx. And again, the reason, if you'd rather actually know exactly why, is because I find the rectangles using the axis that's perpendicular to the axis we rotated. That's how I find the rectangles. If you don't like all that crap, just refer to my earlier way to find out. So we know it's integral dx. That's important to set up early for yourself. That's not a 2, it's an east right there. So if I want to figure out now, so I can put here 2 pi. What's the radius going to be if I start at the axis and I go out to some arbitrary rectangle?
X plus 1.
Yeah, it's got to be, this is x, and then I got to add plus 1, so it's going to be x plus 1 for the radius.
And the X.
And then what is the height going to be? Yeah, it's got to be a function of x, root x. Cool.
Yeah. But it could be anywhere.
Yeah.
Now, for some reason, this throws people off when you go to enter. Now, what's the limits going to be? X is going from 0 to 1. And please, dear God, notice that the limits only care about what your region looks like. All the rotation shit is taken care of by the 2 pi and all that kind of business. So don't, for some reason, people start to think the limits go from -1 or something. Some guys are like, I would never have thought that until you said that. Well, but it's just about the region. That's why you don't have to do any 3D stuff at all. All you need is the region to get things set up. I'm sorry, does somebody have a question?
Yeah, I had a question, but I know.
Sweet. So what I do is just kind of talk over it and then hope you answer yourself. So how do you do this? This throws people off. X plus 1 times x to the 1/2. So it's totally doable. Distribute that x to the 1/2.
X to the 3/2 plus x to the 1/2. And then thingy, and then it's x to the 2/5, or 2/5 x to the 5/2.
Yeah, 2/5 x to the 5/2 plus
2/3 x to the 3/2.
from 0 to 1. And then only 1 matters, right? I like it. Oh boy, that time went fast. Alright. Tomorrow we're going to focus on finishing out chapter 6. I'll have the practice test to give you guys. No, I'm sorry. I'm talking out of my ass. No, yes, I'm fine. Our next test is on the 2nd. I'm going to give you the practice test a little early just so you have more time to put it in a corner. Oh, don't forget, just like it says on the homework sheet, Wednesday is out. I'm giving you that day off because I'm giving myself that day off.
After 6.5, we're done. What about that?
No, chapter 8, we're going to do a little bit.